Record. All right, recorded and is rolling. Welcome to Thursday, August 31st. Yeah, so remember we weren't here yesterday. There was a hurricane day. I hope you guys made good use of that day. Maybe got some rest. Maybe solved some physics puzzles. Yeah, you guys like solving crosswords and Sudoku puzzles. Well, that's what physics puzzles are like, except they're physics. Oh yeah, but not a lot different. Other than hey, you might learn something good out of it. All right, so I got a pair of starter questions. Right, throw a ball straight up at 30 meters per second. What's the maximum height? And then in general, just throw it upward at some initial velocity v naught, which in general, just in terms of variables, can you solve the maximum height? Which is a skill that you have to have in AP to be able to solve things in terms of variables. Right, so these are the same question, specific and general. Okay, we'll look at some conceptual questions real fast. Actually, there's a graph I want to throw here in the middle. We'll do college physics puzzles. I'd like to give you guys some class time. I know we're missing a day, which it's really hard. I really wish we'd been at school yesterday, but well, can't do anything about that. And you guys remember AP Classroom? I still got the same tentative due date, Thursday the 7th. Okay, so that's what's going on there. All right.
But Mr.
Oh, yeah.
What does it ask? You said what is maximum in
Maximum height. Maximum height. Take a baseball, throw it straight up at 30 meters per second. All right, who solved it? Neil, what you got? 45 meters. How'd you know it was 45 meters? All right. Oh, you did it a tricky way. Ooh, I like that. Here, okay, let's do this a couple ways, including Neil's way. Here, you know what? I would do it my way first because I'm up here. But yeah, we'll do it your way too because that was a good trick. All right, so the way I might do it is I might make a checklist, a tax VB checklist. Say like, what do we know? What do we want to know? You know, I should draw a picture too. Okay, so you're down here on the ground. Okay, you throw a ball straight up. I'll call it V naught. Okay. Then it's gonna rise, 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 right, and then start to fall, fall, fall. Okay. The question is like, how high does it go? What's the maximum height? Write that this way. I'll call this H max. Okay. All right. Now, all right. So yeah, different ways you can solve this, and they should all lead to the same answer. Neil told you guys it will be 45 meters for V naught is equal to 30 meters per second. Okay. So let's say we do the checklist method. Right. Remember these 5 kinematic variables we're juggling. Remember I told you if you identify how many of them you can solve the whole thing. Yeah, three you can solve, right? Okay. Yeah. Here. Get some of that. All right.
Let's put this right here.
Yeah, if that works. Yeah. All right. Okay. Okay. No, you're good. You're good. You're good. All right. Yeah. You're in hard times. All right. So, guys, what variables do you know here? What's one of them you know?
Time.
Wait. Well, you can figure that out. But
oh wait, well we already.
I explicitly gave you at least one of these, right?
Oh yeah.
30 meters per second could be the initial velocity. Acceleration. Okay, what's acceleration? 10 meters per second squared. Nice round number. Right. Now, guys, what if under acceleration I put 10 meters per second squared, and under initial velocity I put 30 meters per second? So here's meters per second squared. Here's meters per second. Right. Now, here, guys, there's already something wrong with what I wrote.
Uh-oh.
What's wrong with what I wrote? Gavin. Boom. Guys, here, Gavin. One of these needs to be negative. Because guys, if you throw it upwards and gravity's pulling downwards, that's opposite directions. See, like the way I set this up, I'm assuming either like repulsive gravity, like it's gonna push it, or maybe I'm on top of the cliff and I'm throwing it straight down. Right? Yeah. So, let's now. Can you pick either one of these and make it negative?
The V naught.
Sure. Let's do that. Right. It doesn't matter which one, but once you slap a negative sign on this guy, now we're defining down as positive, up as negative. Okay. Want to have it reverse? Okay. There must be something else you can identify. Guys, what do you know about at maximum? Because aren't we going from this point, bam, to that point, bam?
Bam.
Point A to point B? Okay. What special property do you know defines maximum height?
Gravity.
Zero velocity, zero final velocity, 0 meters per second right here. Right? And once you got that, you guys see we know acceleration, we know the 2 velocities. Okay. So if you want to jump straight to maximum height, which one of these expressions leads you straight to maximum height? Well, the top one, here's the trouble with the top one. There's two unknowns. You guys see x and t? See, we don't know x or t. No, we could figure both of them out.
But, like, can you divide the acceleration by the velocity or something to get the time?
Yeah, actually, you're onto something there too. All right, yeah, okay. So here's what I did. Yeah, because again, there could be multiple ways to do this. I'm gonna jump to this third one. You guys see this third one? Because look, don't we know? Bam, bam, bam. We know those three right there, and we're solving for like a displacement. That's what x is. The displacement could represent maximum height. Okay, so I might do something like this: final velocity squared equals initial velocity squared plus 2. I could say 2ax. You could say 2gh if you like. Okay. So I know this is going to go to 0. Here's your 30 meters per second squared. Okay. One interesting thing to note, when you do break out this third kinematic expression, the fact that you're squaring numbers, you would lose the negative information. You guys see that? Right. That's a good thing to hold on to the in the back of your mind, that you lose the negative information. Every once in a while that runs you into trouble. So careful about that. Okay. 2 times we got 10. Oh, excuse me. I think that meters per second squared. And then where x is, I'll call it h max, because that would correspond to this 0 final velocity. Okay, well, 0 squared, so 0. Okay. All right, so I got 30 squared, it's 900. Subtract 900 over negative 900 meters squared per second squared equals 20 meters per second squared times h max. Divide both sides by 20, 10, 10. Oh, negative 45 is the number, meters is the unit. Right. Wait a minute, should it be negative or should it be positive according to how we set it up? Wait a minute. Which way is positive, up or down? Yeah, we've been defining down as positive. We said we were throwing it in the negative direction. So if you start at ground level as 0.0, actually it should be negative according to the math that we set up, right? So actually this checks out, right? Because up's negative. Guess that, right? You guys get there? Okay. Now, the way that Neil was explaining it, actually, I'm going to show you the way he was explaining it with the graph. Okay. Let's do a v versus t graph. You guys remember v versus t is a very information-rich graph. The coordinates tell you the velocities, the slope tells you acceleration, and something about the area under the curve tells you displacement, which might be what we're looking for in this case. Okay. Meters per second, seconds. All right. Okay. Now, I'm gonna flip the directions. This time I'm gonna call up positive. Is that okay? Up positive and down is negative. Okay. So if up is positive, down is negative, I've got a v naught of 30 meters per second right here. All right. Guys, what's the slope of this line? Meters per second squared. And since we're talking about free fall gravity, the number must be what? Yeah, 10 meters per second squared. Right. Okay, so you guys see that up is positive and down is negative. Right, you guys see that? Positive, negative. All right. Guys, what property of this graph would actually, I guess if you solve it this way, it might be nice to get the time interval first. Right, the time interval. Right. This point on the graph, what does that correspond to with the story? The story of throwing the ball straight up. What point is this right here? Maximum height, right? Yeah. Now, so this is only half the time it's in the air, right? Doesn't the ball actually like fall back down, like something like that? Just keeps on going. Right, keeps going. Right, so here's all the way to maximum height. Max height, 0 velocity. Right, and keeps on. Right. So if you know the intercept is at 30 and you're down 10 over 1, down 10 over 1, down 10 over 1, how much time is that? You guys see 3 seconds, right? 3 seconds, right? Which you could also get with the equation, right? Right. Okay. And now, what's the right? Here's one way to do it. What's the area of that triangle? One half base height.
45.
45, and the unit is meters. You guys see the area of that triangle is 45 meters? 45 meters. You guys see that, right? 45 meters is the right meters per second times seconds gives you meters. 1/2 base height. Right? You guys see that? H max equals 1/2 base height. All right, you guys good? Okay. But what Neil was saying was, hey, if you throw it at 30 meters per second, it's going to 0 meters per second, and it tapers off in a direct relationship fashion, then the average velocity, now here's a really cool trick that's sometimes good to pull out of your back pocket. Your V average, sometimes you see a bar over V for V average. Maybe here, I'll do some redundancy here. Right, you see sub average or a bar, it's the same idea. There's the average velocity. The average velocity for 3 seconds. Okay, hey guys, what's right? What's the average velocity according to this?
15.
Yeah, 15 meters per second, right? 15 meters per second. Right. And if you do that for 3 seconds, what's 15 times 3?
45.
It's still 45 meters, right? You guys see that? Right? Right. So yeah, a little bit different perspective. That's pretty cool too, right? Right, you guys see there? Okay. Oh, could you have used the second kinematic equation and solve for the time first, and then plug the time into this first one and solve for x? Could have done that. Could have done that. Right. Let's do it one more way, which is look at my picture. See how every second I take a picture? Right? Like if you throw it straight up at 30 meters per second, how fast does it move me after 1 second? 20 meters per second. And then 10 meters per second, and then 0 meters per second. See how its velocity is changing by 10 meters per second every second? Right? It's slowed down because it's going up. Okay. Guys, that's how many seconds to get to the top?
3.
3, right? Which then you could solve, this would be 3 seconds, and then you could use a kinematic expression to solve for x, or it's also consistent with this graph being 3 second time interval. 3 seconds. All right, you guys good there? All right, so let's do an extension on this, which is, what about just some general velocity v naught? Right. What's the max height just in terms of any throwing speed? Let's say we all know we're throwing speeds. We all go to back the skull and just start throwing a ball straight up. Okay. So let's get the ground going right here. We got to throw a ball up at some just generic v naught. It's got to reach some h max, and we're going to solve in terms of variables. In fact, let's make it so general that we can even switch planets, right? And we can solve it that way, like on Mars. So we're also going to make the gravity field a variable, right? Right. Let me do my check plus method. Right. So here's our 5 kinematic variables we're juggling. Okay. No, you know this one. Check. You know that. A, let's just call some general value G. Now, one more thing on that. Remember last time we called these opposite directions? Right? Probably a good idea to do the same thing, you guys think? Okay. Maybe just, well, maybe if V naught represents sort of speed, I could throw on a negative to call it velocity. Okay. Okay. And then so check. All right. And then for the scenario, what's the third thing we also know? For maximum height, what's happening at maximum height?
0.
Yeah, 0 final velocity, 0 meters per second final velocity. Check. Right. Now we can still use the you can use the graph method if you like. I'm gonna pick this guy right here. All right, so let's do it. Let's go VF squared equals V naught squared plus 2AX. Okay. VF goes to 0. Guess it's got units, right? Okay. V naught is just V naught because we're keeping it really generic. But I guess I'll make that negative. It's being squared, so we'll lose that anyway. Okay. Plus 2 times, in the place of A for acceleration, I'll do some generic gravity field. So now we can do Earth gravity field, Mars gravity field, the Moon gravity field. We can plug in whoever's gravity field we want. Okay. And X is going to represent H max because that corresponds to the 0 final velocity. Right? That's when max height is reached. VF equals 0 meters per second at the maximum high point. Okay, max height point. Guys good? Okay. All right. Can you guys solve for this H max? What does that look like? I mean, you're just a couple algebra steps away. You guys go ahead and do it on your paper. What's that gonna look like? And this is a skill you have to have for this class to be able to solve in terms of variables. There's no given values there. You're just finding some general expression, like some universal expression you can use to solve any of these. Okay. What'd you guys get? subtract this over, divide by 2g. H max would be g naught squared. It's been subtracted over, divide by 2g. It'll look like that. Right? Now that's if you define down as positive. That's why we're getting a negative answer overall. If you just wanted to go with like speeds and magnitudes, then you could just drop the negative sign, right? You guys get the idea, right? Okay. Right, you guys get there? Right, let's do here, I want to slip in a graph right here. Graph time. All right. Oh, look, it's a scenario in X versus T, B versus T, A versus T. Hey, we did a bunch of these back before the hurricane. So car brakes to a stop. Car brakes to a stop. Oh, you guys draw those 3 graphs before I reveal the answers, right? And really think critically, really try to get to the answer. If you can get the answer before I show you. That's a good sign. Car brakes to a stop. Okay. So I guess at time 0 is already in motion, right? Maybe that's a hint. Oh, I should have added a detail. I should have said brakes to a stop uniformly. Uniformly means constant acceleration. Okay. In this class, very rarely will you ever have a scenario that's not constant acceleration. Okay. So if something is ever speeding up or slowing down, it's doing that at a constant rate. And the physics term for that is uniform motion. If you ever see uniform motion, okay. But that's a going assumption anyway. All right, you guys got those 3 graphs drawn?
I got them.
3 graphs?
All
right. I would take a little more time, but we missed a whole day yesterday. So you guys ready for the review?
I'm ready.
Right. Or you know, you guys tell me what does the V versus T look like? What do you guys draw for V versus T?
That way.
Ah, right, downward sloping. Right, starts at initial velocity, goes to 0. Right. What do you guys draw for acceleration versus time?
That way.
Because if the car is moving forward and it's braking, is acceleration positive or negative? Ooh, negative, right? And the tricky one is X versus T.
That way.
Oh yeah, all right. I like those motions. You guys do like that, right? Here you go. So velocity goes to 0 at a constant rate. Acceleration is constant negative value. Just braking to stop. Right? And hey, is this still a parabola? That is a parabola. In fact, here's the vertex up here. Ooh, that's weird. That's different. The vertex is up here. Right? You guys see how like during the first bit of time, it's moving really fast, so it's going to move really far. And then as it breaks to a stop, like the last increment of time, it doesn't move very far because it's not moving very fast at the same time. Oh, that's why it kind of bends down like that. Right. You guys can figure that out. All right. You know what? Let me do one more poster. I got one more linear motion poster. Okay, this one's a little bit involved, but here's like a pretty universally what you could have for increasing or decreasing velocity. Okay. All right, so I don't have any constant velocity ones on this table, but okay. Guys, velocity could be positive or negative. Acceleration could be positive, negative. I guess acceleration could also be 0. Maybe I should have made a row for that. But oops, I didn't. So we'll go with this. Okay. I guess velocity could be 0 too. I'm not gonna have that. Okay. So what does it mean, guys? What does it mean for velocity to be positive and acceleration to be positive? So you're in a car going faster, right? You're gonna hit the gas pedal. And what are those graphs going to look like? X versus T, V versus T, A versus T.
That way.
Right. So yeah, you have like a positive acceleration. You're speeding up, right? And oh, hey, parabola here. This looks a lot like dropping a rock off a cliff, doesn't it? Moving forward, speeding up. If it's positive, right? Okay. What if you have a positive velocity and a negative acceleration? Oh, isn't that what we just did? With the car braking to a stop. Car braking to a stop. We just did that. Right. Oh, boom. That's those 3 right there.
Oh yeah.
Right. Car braking to a stop. We just did that. Right. All right. Oh, because what does it mean for velocity to be negative? Does that mean you're moving backwards? Yeah. Or at least you're moving in the opposite direction of what's defined as positive. Right? So we're throwing the car in reverse. Right? You guys see how the direction of velocity tells you the direction of motion?
Yes.
Right. All right. You guys are on. So what if you are in reverse Oh, actually, I think this quadrant's the trickiest quadrant right here that we're about to unveil. Okay. But you have positive acceleration. That means you're in reverse and doing what? Slowing down, right, right. That was the trickiest one to figure out, right? Here's why. Guys, anytime your velocity and acceleration have opposite values, like positive, negative, or negative, positive, whenever they are opposite of each other, you're slowing down. Your velocity is approaching zero, right? In this case, from the positive side, in this case, from the negative side, okay? Whenever they have opposite signs. Hey, so if they have the same sign, positive, positive, you're speeding up. What do you guys think? Negative, negative. Do you think you're in reverse going faster, faster in reverse? Exactly. Moving backwards, speeding up.
Wait. Oh, okay.
Right? Because negative, negative, it's all in the same direction, right? Right. You guys think you could probably figure this out? Okay.
Wait, acceleration, if it's positive, why is it staying positive?
This one?
Yeah.
Okay. Yeah. So it's constant acceleration. Now the velocity, like the speedometer needle is going. That's happening at a constant rate. So you are going faster, faster, faster. Okay?
Oh,
it's just the rate that the needle moves is constant, right? It's like the speed of the moving needle. Right? Right. All right. Everybody still alive out there?
I'm good.
Guys do good. All right, so let me switch my screen over here. I know I'm really going faster than I ideally like to, but yeah, we got hurricane fun times and kind of stuff.
Oh yeah.
Where's share screen? Here we go. All right. We're not actually gonna play the Kahoot just because I'm trying to save a little time. Sorry, guys. But guys, these questions are the same as remember the page with the boxes on it, and flip it over to the other side. The conceptual questions there. These are the same conceptual questions. Right. So yeah, if you want to follow along, right, guys. One possible unit of speed. Speed. What gives way speed? Is some kind of what per what? Meters per second works. Distance per time, just in general, right? Like miles per hour. Just right. You got miles per hour, kilometers per hour, light years per century, meters per second is our go-to, right? But they all work. You guys see how all the above work? Right. Object moves 5 meters in the first second, 5 meters in the next second, 5 meters in the next second. The question here that got cut off a little bit is what is the acceleration? Oh, 0. All right, you guys got it. Right. You guys see the velocity? The velocity would be what? 5 meters per second. Right. But there's no change. Because there's no change, the acceleration is 0 meters per second squared. Because there's no change in its velocity, right? In fact, inside that car, you would feel a lot like just sitting in this room, right? A giant spinning planet. As an object falls freely in a vacuum, it's what increases? Velocity or acceleration? Velocity, right? And velocity picks up at a constant rate. Does acceleration increase?
No, it
stays the same. Constant acceleration. Like for Earth, it'd be like 10 meters per second squared all the way down. Right? Again, as long as you're in a vacuum. Right? Yeah, velocity is constant. Or sorry, I'm so sorry. Acceleration is constant. Velocity increases at a constant rate. Okay, so velocity increases. Okay. Right. Ball is thrown straight upward and is caught when it comes down. In the absence of air resistance, I think this one says the speed that you catch it compared to the speed you threw it. Guys, if you throw here, let's go back to one of these notes pictures over here. Let's do this one right here from earlier today. We have a screen back over here for the Zoom. There we go. Okay. So guys, suppose you throw it up at 30 meters per second, and then you guys said it goes 20 meters per second, 10 meters per second, 0 meters per second. Then it starts to fall. How fast right here? 10 meters per second, then 20 meters per second, then 30 meters per second. The directions just switched, right? Like when it was going up, obviously it was upward. When it's coming down, it's downward. Okay? But the speed is the magnitude of velocity. Right? Because when you catch the ball, does it have the same speed as when you threw it?
Yeah.
Sure does. Sure does. Right? In fact, the graphical version of that is, remember, this graph so far up to this point only tells the max height point. If you could continue this graph, go like this, right? So that by the time you catch it down here, it's at v final equals negative 30 meters per second. Right, is when you catch it, right? You guys see it? This 45-meter triangle up and this negative 45-meter triangle down brings it exactly back to the location where you threw it. Right? You guys see it? All right. All right. A ball is thrown straight upward and caught when it comes back down. We just did that one. Right. So the same speed, same speed it's supposed to say is when it was thrown upwards. Right. So questions get cut off a little bit, but you guys have the questions printed out. Okay. Ball thrown straight upward rises and falls back to the floor. During this time, the acceleration is always
10 meters per second squared.
10 meters per second squared. In which direction? Down. Right. Wait, when the ball's moving up, does gravity still pull down?
Yes.
Yeah. When the ball's moving down, does the gravity still pull down? Yep. This time the acceleration is always, 10 meters per second squared downward. Right? Right. Suppose you travel 300 kilometers in 5 hours. What's your average speed? 60 kilometers per hour. Right. Guys, in this class, the vast majority of the time, do we care about average velocity or instantaneous velocity? Instantaneous, right? What goes in? What feeds into all those equations? Instantaneous values, right? Instantaneous, right? But know what average is? You might get an average question here and there. Right. Ball thrown straight up at the top of its path. Its instantaneous speed is how much? 0 meters per second. Ball thrown straight upward at the top of its path. Its acceleration is how much? 10 meters per second squared. Which direction? Down. All right. About 10 meters per second squared. There you go. Oh man, you guys are winning. A car accelerates at 3 meters per second squared. How long does it take to get up to 15 meters per second?
5 seconds.
5 seconds, right? Yeah, you guys just do v equals at, right? Yeah, if it starts from rest, right? Just v equals at. Yep. Right? 3 times 5 is 15. Yep. Right? Oh, 5 seconds. Look at you guys go. Look at you guys go. Freely falling object starts from rest. After falling for 5 seconds, its speed will be about how much? 50 meters per second? It's 10, 20, 30, 40, 50. You guys remember, that's still on this table right here, isn't it? You guys remember this table? Drop a ball off a cliff. After 5 seconds, it picks up to 50 meters per second. Hey, I got another question for you guys. That same ball, how far did it fall during that same 5 seconds?
125.
About 125 meters. And how would you know that?
College.
Yeah, college. That's the answer. Yeah. Okay. So it's actually x equals 1/2 at squared, right? Right. That's the college equation. And also the chart. Oh man, so many ways. They all lead to the same thing. Right. So 5 seconds it falls, picks up to 50 meters per second, and it fell 125 meters. Right. When you look at the speedometer of a moving car, you see that car's what? What does the speedometer tell you? Does the speedometer tell you
the speed? Velocity.
Yeah, okay, instantaneous speed, right? You guys get instantaneous speed? It doesn't say average speed, right? It says instantaneous speed. It tells you how fast you're going at that instant, right? Okay. A car starts from rest. After 5 seconds, picks up to 30 meters per second. Well, first question, how much time did it take to do that? 6 seconds? I forget what this question is. Yeah, so it takes 6 seconds.
No, it's just
it might ask
6 meters per second.
How far did the car go? Here. 1/2. Okay, I gotta calculate this myself. How far did the car go? Maybe I'll use VF squared equals V naught squared plus 2AX. No. Okay, I have to solve for acceleration first. VF equals V naught plus AT. Take seconds. Huh? It might be. The question was just acceleration.
Call it.
All right, so yeah, 6 meters per second squared. Yeah, you could do VF squared, that's 900, equals V naught squared, which would be 0. Okay, so plus 2AX divided by 2 times 6, that's divided by 12. I'm getting 75 meters, I think. All right, anyway. Make sure I did that right. 2A. All right. In a vacuum, Objects fall at constant what?
10 meters per second squared.
Which is a type of what? Is that a velocity or an acceleration? Acceleration, constant acceleration, right? The velocity is changing. The velocity is just changing at a constant rate. The rate of velocity is acceleration, right? Right. Oh, you know what? Side note here that's related to this question. One of my kind of pet peeves as a physics teacher is whenever I'm like watching something on TV, or like, and the plane in the air or the vehicle took off at a high rate of speed. That's always like, because guys, rate of speed is not speed. Rate of speed is what? Speed. Acceleration. So if you're ever a narrator for one of those programs one day, just say it took off at a high speed. As drops of water fall from a leaky faucet. Right. They go down. They do go down. Now, let's look at this picture right here. You guys see this rock falling off this cliff? Yep. Does that look like drops of water from a leaky faucet? I see. Do they kind of like spread out as they're falling down? Right? Get further apart as they fall. Right? Kind of like dropping the rock off the cliff. You guys are winning all these. Bob can jump off the ground with twice the jumping speed of Alan. Just after his feet have left the ground, what is his acceleration compared to Alan? Wait, do they have the same acceleration? Yeah. Yeah. Even though they're going different speeds? Because they're 10 meters per second squared. Yeah, there you go. And there's the value, right? 10 meters per second squared. Yeah, equal acceleration. Downward acceleration is equal. Okay? Doesn't matter how fast, doesn't matter what direction. What is the value of G at Earth's surface? 10 meters. Boom, there you go. About 10 meters per second squared. Okay? If you guys are in a university class someday, they might tend to use 9.8. Every once in a while, you have a material that has 9.8 on it, but you guys got it. Ball dropped from the top of a cliff. Each second, its speed increases by how much? 10 meters per second squared. Yeah, so 10 meters per second per passing second. Right, so there you go. Right. You drop a feather and a coin in a vacuum chamber. Which one hits the ground first? Same time. Did I show you guys the bowling ball and the feather in the vacuum chamber? All right, all right. Projectile fired straight upward at 30 meters per second. Hey, just like our starting question. Right. How much time to return back to the ground? 6 seconds? Because we already figured out earlier today, it takes 3 to go up. So three back down by symmetry. Now there are lots of ways to solve that. You could break the problem in half, so to its maximum point, it would be 3 seconds, and then double that. I like to do it that way. You could also say, guys, if you throw it up at 30 meters per second, it's hitting your hand how fast again? Yeah, negative 30 meters per second. So could you do like VF equals V naught plus AT, and then you'd still get 6 seconds, right? There's multiple ways to solve that. Okay. Last one. Oh, here's a good challenge question here. Suppose a jumper claims a hang time of 6 seconds. Now it's kind of ridiculous that you jump off the floor and it's not 6 seconds till you hit the floor again. Let's just run with the numbers. It's just a mathematical question, right? Okay. I don't know, maybe it's a little kid. Like, I can jump for 6 seconds. If this is true, then that jumper would be able to jump to a height of what? You leave the floor, you don't get back to the Earth's surface until 6 seconds later. 45 meters. How'd you know it was 45 meters? Divided by 2 for the up and down. Oh, perfect, perfect. Yeah, this is also in line with our starter question, isn't it? Right? Because guys, if you're off the floor for a total of 6 seconds, that means 3 seconds up and 3 seconds down. Right? And you say, hey, I know if I dropped a ball in 3 seconds, it would fall 45 meters because 1/2 AT squared. All right, all right. Look at there, 45 meters tall. I can jump 45 meters tall. All right, you guys good? Right. All right, let's flip back over here. Done. All right, let's look at these college physics puzzles. All right, so you guys remember I gave you guys this page a while back. Now, some of these are circled. Guys, all the circled ones are the ones I'm going to pick up for your homework. Okay, you guys do this? Right? Right. Now, I want to help you guys out a little bit here. Now, I could write them all down as I go, but we got really limited time. So here's what we're actually going to do. I'm going to go through the starred ones and the circled ones, and I'll read these and show you guys the solutions. You guys do see the solutions are on your desk, right? You guys see the solutions on your desk. They're also on Google Classroom. But I told you guys before, there's a proper way and an improper way to use the solutions. The proper way is you try to solve it all by yourself just on a blank piece of paper.
And the improper way is copy the math.
Yeah, exactly. Oh, you guys remember that. Yeah, the improper way is just to turn your brain off and just copy them, right? One way you're learning, one way you're failing. So number 5 is the first starter one. So I just want to at least mention all the start and circle ones. 2 boats start together, race across a 60-kilometer wide lake and back. Boat A goes at 60 kilometers an hour there and back. Boat B starts off slow at 30 kilometers an hour, realizes it's getting behind, and then comes back at 90 kilometers an hour. Which boat wins, and what's the average velocity of each winning boat? So 2 questions there. So first question, which guy, intuitively, who do you think wins? 60 and 60 or 30 and 90? I'm talking about kilometers per hour.
Oh, it's tie.
Here, let me see, show hands. Let me show you guys. So one boat goes across at 60 kilometers an hour, comes back at 60 kilometers an hour. The other boat takes off at 30 kilometers an hour, and then hits the other bank. It comes back at 90 kilometers an hour. Right?
39.
Oh, show hands. How many guys think it's a tie?
Tie.
Nope. How many guys think the constant velocity, the constant speed boat wins? Nope. All right, there's my winners right there. You guys are the constant speed boat. Okay. Now, how can you solve this in terms of physics? Guys, we're in a boat race. They're going the same distance, right? Same distance.
Yeah.
Different speeds.
Yeah.
What physical property tells you if you won the race?
So less time.
Less time. Exactly. Less time. So let's take a look at the solutions. I got distance equals speed times time, right? So can you switch that around and get time, therefore, would be distance divided by speed?
Yep.
All right, here's the 2 halves of the race for one guy, 2 halves of the race for the other guy, and you can solve for the amount of time.
Yep.
Guys get that? Yep. All right. Number 6, a graph shows displacement versus time. Ooh, look at that. For a particle traveling along the x-axis. So this is one-dimensional motion. It's just moving like forwards and then backwards. And then forwards again, right to the tail end there. Oh, whoops. I forgot the other question about the boats. Guys, if they both start and end at the exact same location, what is their average velocity, technically?
0.
Yeah, 0. There you go. Because technically they have 0 displacement divided by some time interval, so 0. Okay. So now the graph one, x versus t. It asks for a bunch of average velocities.
Okay.
Guys, average velocity. Can you pick like, let's say like this point here and this point here, and then find the slope between those 2 points?
And the middle.
Right, because the slope of x versus t would be something about velocity, right? Okay. Now that's average velocity, which I said we don't very much care about in here. Right? But number 17 also refers to the same graph and asks about instantaneous speeds.
Yeah.
Guys, instantaneous speed, is that like the instantaneous slope here?
Yep.
Instantaneous slope here. Could you guys do like rise over run, blah, blah, blah? You guys can do that, right? Any question about the difference between average speed and instantaneous speed for x versus t graph? Right. Number 20. I did write your guys' quiz yesterday. That's one thing I did with my time. And number 20, I wrote a very similar quiz question. Number 20. Number 20. Do you guys see an acceleration versus time graph? And look, constant acceleration for the first interval of time, a different constant acceleration for here, and then just different acceleration here. Okay. Now in the solutions, I solved this algebraically. Let me show you guys what it looks like in the solutions. I used those kinematic equations. Right, solving for v, solving for x equals v naught t plus f a d squared. I think there's a more efficient way to actually solve this problem, okay? Which is to make a different type graph. Guys, the question is, what's the distance? What's the distance it travels? And I think the better way to solve this is to think about this graphically. So we're going to do this right here. We go x versus t, b versus t, a versus t. Okay. Oh, whoops. Let me back up. Okay. Meters per second squared, seconds. That's our classic 3 graphs, right? Right. Now here's I'm not going to draw exactly what they gave me, but I'll get it pretty close. They said you start off with some positive acceleration. They didn't say start from rest. Guys, start from rest means, this point right here, right? Right? So they did have to give that to you. Right? Then it like drops off, and then you go like constant acceleration for a while. Now, if this was a math class, they might call that a jump, and you need like a pole or something. But, physics.
Open circle.
Yeah. Physics is more like you can take it or leave it. Right. Right. Then it jumps like way down here, right?
Yep.
Right. And then it goes back up here. Right. All right. So they gave you an acceleration first time. It looks kind of like that.
Yep.
Right. And the question they asked is like, how far does it travel during that time interval? Guys, isn't that bam, bam, 2 steps away? Right. Again, you could solve with the equations. That'd be fine too. Right. But the way I'm showing you right now, I think is the better way to solve, or the more efficient way to solve it. Right. What does this graph look like?
Different slopes.
Yeah. Tell us A1. Isn't this the slope of this guy's A1? It only goes up to right there. Then there's this middle interval where there's 0 acceleration. Guys, 0 acceleration. Does that mean that the object came to a stop? Oh man. How to get such a smart class this year? Were they like saving you all for this year? They're like, here's all the smart students. We'll just put them all in the 2023, 24 class. Right. Okay, that's how these things work, isn't it? Okay. And then, okay, so it's still moving, right? Still moving. Right. So still gaining displacement for that matter, right? Right. And then, guys, the negative acceleration. What's that going to look like on V versus T? Yeah, slowing down. Now, if you look at the sizes of these rectangles, you guys see how there's a big old rectangle here and a smaller rectangle here? So at the end of this interval, does it go exactly to 0 velocity? Is it still moving forward or is it moving backward? It's still moving forward because this rectangle is larger than this rectangle. That means it gained more positive velocity than it has negative velocity, right? So there's actually it's not even quite a trapezoid, right? But you see a triangle followed by a rectangle followed by like a trapezoid type shape right there, right? Oh, what property of V versus T tells you displacement? The what? Area under the curve. So here's what your X versus T looks like. Parabola, and it takes up a straight line, then it slows down like the car braking to a stop. Except it doesn't actually quite come to a stop, right? Not for this particular one. Right? You guys can figure that out? You guys can figure that out? Right, everybody okay? All right, what else we got? 22. Average person passes out an acceleration of 7 Gs. Suppose you were in a car going like 0 to 60. How much would you have to? How much time would that take? You guys ever heard of like G-force or G's? What guys? What is 1 G? How many meters per second squared? 10 meters per second squared. Hey, are we sitting in 1 G right now? We are. So if you're going 7 Gs, how many meters per second squared would that be about? About 70. Okay, it looks like in my notes it did 68.6, but you round that to about 70, right? Okay. Could you translate miles per hour to meters per second? And then do a kinematic equation and solve for the time interval? You guys can do that, right? All right.
I'll know about that.
24. Oh, look, it's a velocity versus time graph. Velocity versus time. And they ask a bunch of questions about acceleration. Now, if they say average acceleration, can you pick 2 points and then find the slope of the 2 lines that connect? But they do instantaneous. You gotta do instantaneous there, instantaneous slope there, instantaneous slope there. You guys can do instantaneous slopes, right? All right, 27. Object moves with uniform acceleration. Has this starting velocity, goes from this coordinate to this coordinate. What's the acceleration? Right. Here's where I want to modify something. You guys remember these kinematic equations? This x, the way I write it, really represents a displacement. It's like a difference between 2 points. It's a displacement. Yep. AP, if you look really close on their equations, they actually write a little bit different. They do this. They do x final equals x initial plus v naught t plus half at squared. Now, if AP writes it like that, they're not talking about x's displacements. They're talking about exact positions. You guys see that? But see if you subtract the initial position over, you get x final minus x initial equals, right? And then it just goes into this. Right? Some textbooks write it this way. They say delta x equals v naught t plus f a t squared. Right? I just go with x, but really I'm talking about a displacement. You guys see that versus a position, right? Just think about these things, right? I think you guys can navigate that. All right. 34. Jet plane lands with some speed and can slow down at some rate, which is a negative acceleration. That's the rate it can slow down. 2 questions. How much time does it need to come to rest? And how much distance does it need to come to rest? Can you guys just pop into here and get the answers?
20 seconds.
Maybe make some graphs. That might be the answer. I don't know. Right?
I think so.
All right. 35. 35 is on the quiz. Speedy Sue travels at 30 meters per second, enters a 1-lane tunnel. She observes a slow-moving van going only 5 meters per second. Oh no, that's a lot slower. She's about to rear end this guy. She applies her brakes, but can only slow down at -2 meters per second square because the road's wet. I guess it rained inside the tunnel. I just realized. I don't know what's going on there. Will there be a collision? How will you decide? Guys, if there's a collision, that means they're at the same what at the same what? Same place, same time? Same place, same time? All right. Now, obviously, you have the solutions. They're on Google Classroom. They're in front of you right now. Right? But this is a critical thing question. Guys, this is going to be a system of equations. Here's the system. Here's Speedy Sue. She's going 30 meters per second. That's initial velocity time plus 1/2 at squared. And the acceleration is negative because she's slowing down. Maybe just say minus 1/2 at squared. You can do that. Okay. Here's the van. 5 meters per second times time. Let's also give them a head start. Can I do this? Give them a head start plus 155 meters, right? Right. And then finally, they're at the same place, same time. Can you guys solve a system of equations?
Yes, I could.
All right. A ball is thrown upward at some speed. How high does it rise? And a bunch of follow-up questions. I think that's very similar to our starter question today. Okay. Ball thrown downward with some speed from some height. How much time does it take to hit the ground? That sounds very equation, right? That sounds very much just pop, pop, get the answer. You see that? Baseball hit so hard, it travels straight up after being hit by that. A fan observes, takes 3 seconds to reach its maximum height. How fast was it hit to get there? And how high does it go? You saw that too, right? Just equations, or maybe like graphs, equations and graphs. Guys, number 59, number 60 are also on the quiz. All right. I think we made pretty good use of our time for Mrs. Birthday Day. You guys have a great rest of your Thursday. See you Friday. And more fun times tomorrow.